postdoctoral research from the National Nanotechnological Laboratory, Italy, CNR INFM Italy, and Indian Institute of Technology Italy. He has been awarded with the number of awards like Sri Ram Arora Award by Mineral Metals and Material Society, Warland USA, DABRNS Young Scientist Research Award in 2011. Dr. Deka has published more than 65 research papers in different international journals of high repute, 2 patents, and wrote 2 books and 2 books chapter published by the international publisher. I will also like to introduce our second chairperson, Dr. Alexander Gree. Dr. Alexander Gree is a professor in the Department of Chemistry, the City University of New York in the Brooklyn College. He did his postdoctoral from UCLA and PhD from the University of Wyoming in 1996. He has many publications in reputed journals, edited many books and book chapter. Please, Dr. Alexander, come on the dais. Come on the dais. Now, I hand over the session to the chairperson.
Yeah, thank you, and a very good afternoon. We are going to start this post-last session. So, first speaker is Professor R.P. Singh, Ravi P. Singh. He's from IIT Delhi. Currently, is a professor there. In brief CV, he has done his bachelor degree from UP College Varanasi and master degree from BHU, and then he later moved to IIT Kanpur for his doctoral studies under supervision of Professor B.K. Singh, one of the well-known person in India. And he has done then postdoc from USA, from Harvard University, from 2005 to 2007. Then he moved to Brandeis University again for postdoc from 2007 to 2011. Then he started his research career as an independent researcher at National Chemical Laboratory, NCL Pune, where I have done my PhD also there in 2011, and then he moved to IIT Delhi in 2013. His in research interest is basically asymmetric catalysis, CH activation, and total synthesis of small molecules. May I request now Professor Singh to please deliver the talk, and your talk is for 20 minutes for your presentation and followed by 5 minutes for discussion. The dais is yours.
Thank you, Mr. for the introduction, and thank you.
Hello.
Okay, thank you, Sabeka, for the introduction. And the outset, I would like to thank Dr. Pratibha for this opportunity. Today, I'm going to discuss some of the research endeavor we are, pursuing at IIT Delhi. Before going to detail, that 3 sub-area we explore there at CCSL, that is our lab's name, and primarily we focus on asymmetric catalysis using chiral organic molecule and the CH activation and photocatalysis. These are the 3 areas where we focus. So before going to detail, if we talk about the synthesis of chiral molecule, as we learned from our textbooks, can be synthesized from the resolution of racemic mixture. That is the one way. Another very straightforward technique is to do selective synthesis. That will give you. The third technique can be that if you take a kind of molecule and desymmetrize it, introduce chirality by desymmetrization process. That is the way you can also make the chiral. In today's talk, I'm going to discuss about that how from a racemic molecule by doing desymmetrization you can induce chirality. So let's look over it. That to make you more familiar with this concept, you can see here that I have taken in this cartoonic presentation, there is apple, and that biter is having 2-prong approach. He is using his hand and mouth, and he is creating what? Basically, he is creating asymmetric. This apple is becoming now change in the shape, and similarly if you remember, generally in the movies that, the always hero says that, be, good with me, otherwise I will break your cemetery. Like, there's, most of the, you can see that, Hollywood movie, this is a very famous dialogue. So cemetery is very kind of organized, and if you break from that, a kind of a construction, then it can create like, asymmetry. So let's talk about that. Why it is important? It is important because it is easy to synthesize racemic molecule without much kind of like, involvement. And then if we break that racemic molecule, which is having kind of like, break the symmetry over there and bring the chirality in that molecule in the kind of advanced stage, and further utilizes for the small molecule synthesis or for the synthesis of like, drug candidates. That can be one very kind of like, economical approach. So can we see that, my lab got interested in especially like, fulvene kind of a structure, because fulvene, if you see that, it has been very less explored. However, it has like, huge representation in the, drug candidates. Is the anti-inflammatory molecule. There's a chiral acyl fulvene, antiviral candidate, enmindenol, and anti-cancer molecule. Not only these kind of like, pharmaceuticals, but also if you see materials, in case like, electrochromic materials where AN2 and AN3. What is common in all these structure is that you fused, basically fulvene core is kind of embedded in the, polyaromatic hydrocarbon. So how to synthesize, how to like, kind of like, install this kind of structure? And to do so, we wanted to use binylogous strategy. Binylogous strategy, I would like to give here again some background of the binylogous strategy. Binylogous strategy, where like, you use binylogous nucleophile to do reaction. And binylogous nucleophile, basically you can see in literature from the silyloxyfuran, butanolide, and like the lactam, all these acyclic, binylogous nucleophile. We were interested in basically this advanced binylogous nucleophile, 3-methylcyanocoumarine. If you see over here that this CH3 is acidic enough, and under, kind of ambient condition, it can generate the corresponding innovate, and that innovate can do, carbon compound forming reaction. We wanted to explore this one, and when we did with the another acceptor, basically that, 1,3-dienone, cyclopentenone, here what happens that it leads to the formation of, fulvene, aminofulvene. This aminofulvene, what is happening in this process? Basically, if you pay attention, the major change is happening that this is the 5-membered ring. This 5-membered ring is getting converted to the 6-membered ring, and at the same time, if you see, the chirality is getting induced. Here the racemic center is there, but in this molecule, it is becoming chiral. How is it happening? In one, go, how this like, kind of assembly is forming. To look over is that, as I mentioned, that, the silent feature that ring is getting enlarged. What are the synthetic tool to enlarge the ring? That is the question posing. And not only that, the major question is that if you want to enlarge the ring with the chirality, that is the big challenge. And here to demonstrate that, you can see here, classically, basically the ring enlargement is done from the cycloalkanone by using under strong basic condition, one can convert into the ring enlargement. Another by using diazoketone, by using sulfone, by a very strong base, and triazole, benzotriazole. All these conditions, classical approaches, require very strong basic condition. And if you consider the case of diazoalkane, that is very, very challenging, because handling diazoalkanes at the practical scale always pyrophoric, and it can be dangerous. However, so there is always need for a like, user-friendly condition where you can cover a very broad substrate scope and you can do the ring enlargement. That is the classical approach. But if we look over another, like, how one can, attain like, enantioselective ring enlargement, to do so, you can see here only 3 reports so far. One by the Feng et al., where he used this, scandium triflate derived N oxide, that, he's a chiral N oxide scandium triflate catalyst to do in ICHE ring enlargement to get this basically pyrimidinone kind of structure. Another from Boston College, Kingsbury et al., what he did use, like, again he used like, aluminum derived kind of vinyl based catalyst, And similarly, Maruka et al. He did basically ring enlargement by using bienal titanium complex to get. These are the only 3 reports where the chiral ring enlargement. Here, what is happening? Basically, again desymmetrization with the ring enlargement is happening. Our strategy is very similar to that, and when we used chiral organic molecule as a basically the promoter or catalyst for this transformation, what did we find? That after the solvent optimization and catalyst optimization, we learned that basically dipeptide thiourea catalyst, this C6 dipeptide, you can see the tert leucine derived, one peptide bond is there, and this is thiourea, dipeptide thiourea catalyst, that gave 97:3 enantiomeric excess and 76% of yield. I don't want to go to the details, but you can see here the most champion catalyst, cinchona alkali derived 9-quinine derived, and the corresponding sparamide catalyst, or even tert leucine derived catalyst did not give the promising result. So with this optimized condition, now I think I have made enough curiosity in all of you that how this transformation is leading to such a fused polycyclic scaffold. How is it happening? It's in a domino process. You can see over here that this binylogous nucleophile is getting generated under basic condition, and first transformation is binylogous Michael reaction. Binylogous Michael reaction sets the chirality. What does it do? It takes this acceptor and it kind of differentiate the phase. This 1,3-diketone, it differentiate the phase, and the first Michael reaction induces chirality. Then the second Thorpe type reaction is happening, followed by intramolecular aldol reaction. That intramolecular aldol reaction generates the cyclopropyl alkoxide. The cyclopropyl alkoxide again goes for the ring expansion, and it goes intramolecular Mannich reaction, and that leads to the ring contraction, and then further again it ring opening and creation of in presence of silica, that aromaticity gets gained, and that leads to the fulvene. It's a very unique protocol where you can see that 7 to 8 steps in continuation in a domino fashion it is taking place, and that leads to the formation of. And visually it appears that these kind of nucleophile can go for 4+2. We thought that it will be going for this aniline formation. However, it leads to it goes for this domino process, and that gives the beauty of these molecules are they are very kind of having very strong dye property. You can see here even the micromolar concentration gives very strong indigo color, and you can see here that it works perfectly fine with the substituted methyl cyanomethyl coumarin. You can see here electron donating methoxy group at the 6th position, T-butyl group, electron withdrawing group, electron donating methyl group, all works. Electron withdrawing halides works perfectly fine irrespective of the position. You can see locations are different over here, and that gave very high enantiomeric excess for all this transformation with this dipeptide catalyst. Not only with the variation in case of this 1,3-diketone acceptor also. You can see here for the aryl core hydroxyl substituted or aliphatic substituted as well as propargyl substituted, and different kind of it works perfectly fine with the aliphatic substitution also here. You can see here 97% appeal with the 92:8 enantiomeric, which is very challenging. Generally, I will show you in the further slides that how the structure of the 1,3-diketone is also detrimental in getting high selectivity. With the ester molecule as well as heteroaromatics is work perfectly fine. With the we have also with this 1,3-diketone with the third natural products and basically pharmaceutical molecules, and you can see here that these opens avenue that one can do transformation at the very advanced stage by tethering these kind of molecule, small molecule, and you can make the next generation of library. That's what I want to pass on over here. You can see palmitic acid, indomethacin, and naproxen. All these do not kind of perturb the selectivity of this reaction, as well as cholic acid and gemfibrozil. In all these cases, E and the DR remains very promising, and to test that these adducts can bear the regular group transformation chemistry, we tried some of the transformation, and you can see here that here we have converted into the thiourea by treating it with the isocyanate, and we have also done converted to the corresponding bromo compound by doing diazotization followed by treating with the BR, and we have also converted into amide. We have also tried to reduce it by treating it with the hydroxylamine, and then here I have not mentioned, but one can convert into the reduce this carbonyl to the CH2. Also one can do that high temperature reaction to add benzyl group over here without any loss in the selectivity. This scaffold works perfectly fine. I mentioned that how this reaction is approaching, how this selectivity is coming. As I told you that basically 1,3-diketone goes and by the bifunctional catalysis is plugged to the thiourea, and then it differentiate the phase, and on one side only attacks happens. You can see here the two phases I have shown over here. In one, phenyl is very close to the trifluoromethyl, this one, and this interaction basically leads to the high enantiomeric excess. This is the favored one, other one is not. You can see here that where it goes. To make sure that this kind of interactions are fruitful, are detrimental for the high selectivity, when we tried with the unsubstituted without the CF3 group, that yielded poor enantiomeric excess. That is the very strong hint regarding this. And now I will switch my gear to the, you saw that how beautifully we have made the chiral fulvene unit. I will switch to the spiro unit. Basically these are the you can see why spirocyclic. Spirocyclic molecules are very unique for giving bioactivity because of their constant structure. They can fit in the you can say that pockets, biopockets very effectively, and they respond very strong interaction. However, making this molecule is very challenging because of their very unique scaffold. Here are few molecules. You can see that fredricamycin, which is antibiotic drug molecule, ecutimine, intracarinone. What is common in R benzoyl A? Spiro P and Spirix, these two are the chiral catalysts we very often in the transition metal derived catalysis we use as a chiral core. You can see here in all these molecules what is common, that this is spiro structure. This is a spiro structure. In this case 5,5 nonane core, 5,5 nonane core. This is the common. So what is question here, that how to install a nonane core, 4,4 nonane core, how one can nonane core one can install. If we have a methodology to install this kind of core, it can make our synthetic strategy very easier. If we look over the prior art, that what is the state of art in this direction, only one report is there for 5,4-decone. Pay attention that I mentioned that 4,4 nonane core. Only one strategy is there for the spiro 5,4-decane core. There is no report for spiro 4,4 nonane core. So we thought that we can kind of address this, and when we looked over literature, that what is the report even nearby, there is one what I mentioned, that 5,4 decane structure by the Janardi in 2014, and 2022 another colleague from the IIT Madras, he reported that racemic synthesis of spiro 4,4 nonane core. We thought of exploring this molecule, and then when we used our organic catalyst for this transformation, we got 4+1 spiroannulation annulated adduct in very high selectivity. And how does it happen? This question comes from the UG textbook learning point of view. If you pay attention, two kind of basically that innovate are possible over here. And once this active methylene groups gets deprotonated, vinylogous nucleophile forms. This vinylogous nucleophile can attack over here. Once it attacks, the second attack is possible, that kinetic enolate can form, and that kinetic enolate can lead to the 4+2 kind of adduct, where thermodynamic enolate can lead to the 4+1. So what is required, that we need to generate a thermodynamic enolate which can jib the reaction and get the spiro nonane core which is required. So we optimize our reaction condition accordingly, and you can see here in first instance we got this champion catalyst, which is having dipeptide thiourea catalyst. It gave 85:15, very nice lead, 70% tilt. Further solvent optimization, it leads to the as well as that tertamine part optimization gives the 98:2 enantiomeric excess for these molecules. Once we have optimized condition, we further looked over the substrate scope. As I told you that it is very important to display that how far this methodology can accommodate that variation in the substrate. You can see here in this case we have bared all kind of substitution on the 1,3-diketone core. Here only few I have mentioned, irrespective of their electronic nature. Nitro group highly polarized, CF3, bromine, all substitution works without, very well, and the selectivity also remains in 90s. We have also shown that di substitution works perfectly fine, as well as heteroaromatic substitution works perfectly fine. And as I showed in my previous problem that even the pharmaceutical and natural products can be tethered and they can be processed for without any change in the selectivity. It works perfectly fine. With all these optimization, we showed that chromonone derived nitrile, alkyl nitrile works perfectly fine, and these thiol. The challenging over here is that these heteroatoms starts participating in the hydrogen bonding and they perturb the chiral pocket. However, we were able to get very practical selectivity here over here with the chromonone derived and selenochromonone derived catalyst.
Excuse me, sir.
Yeah.
You have 5 minutes.
Just I'm closing that. To show that how one can apply this methodology for the small molecule synthesis, we try to do regular group transformation chemistry. Over here you can say that ketamine has been hydrolyzed to give the corresponding ketone. We have also converted reduction of ketamine to get the chiral amine over here with the very high selectivity, and we have here make the tricyclic core, which is constant tricyclic core over here by having special substitution benzoyl group, and that benzoyl group gets fused in the presence of ammonia and forms this immunal kind of core with high selectivity. We have also shown that this is the side half can lead to the third ring formation. Upper half also you can say that is that you have that ketamine substitution with the ester moiety, ketoester moiety, that can get cyclized and it can form another ring. I hope I am able to convince you that these kind of special cyclic structure, polyaromatic hydrocarbon with the fluorine ring, as well as spirocyclic structure with the very high selectivity one can attain by using these organic molecule without using any kind of special condition, no anhydrous and nothing. User friendly methodology can be developed. Here you saw in all those methodology I broke the basically symmetry of cyclopentanone, 1,3-diketone, their racemic molecule, I broke that. Here also you can see here by the binylogous reaction by using maleimide, one can do the binylogous Michael reaction. What is challenge over here? That the same molecule can give racemic mixture. How will it give racemic mixture? It has C2B symmetry, and C2B symmetry comes over there that the two reaction center. You see that this molecule is having C2B, so if reaction happens from the both sides, it will end up with the racemic mixture. But if you differentiate this coordination of these ketone group and only one gets facile for the Michael reaction, that will make the life easier and it will give only the chiral molecule. That's what we target, and you can see here in the optimized condition by using in earlier examples I showed that tert leucine derived catalyst did not work. However, here in tert leucine derived thiourea catalyst work perfectly fine at negative 10 degrees centigrade. It gave 97:3 enantiomeric excess and very high yield. We have also shown over here that what is detrimental that aryl substituted with the 3,5 position. That is required because it flanks like that. That maleimide is like this and this 90-degree perpendicular. So once it coordinates and these methyl groups are flanking like that, so it does not allow that it gets hooked up and attack from the other side. That's what happening over here. We also showed that not only methyl substitution with the chloro substitution and tri-alkyl substitution was perfectly fine with this catalyst. We have also transformed with the regular group transformation chemistry. We created new heteroaromatics by treating it with the sulfur 8 by doing Falconer kind of synthesis of the thiophene. What is happening? I want to give you, if you remember in the very beginning slide, I showed you that bifunctional approach, that person is eating by apple by the hand. Bifunctional, I'm correlating over here that two reaction side. One is like thiourea and other is tertiary amine. Tertiary amine, basically what does it do? It deprotonates. It deprotonates, then it creates innovate. Once it makes innovate, what is needed? The other, like coupling partners should come close to each other, and that approximation should lead. Here you can see that HRMS titration, thiourea catalyst comes over here. In peak D is responsible for the catalyst with the acceptor, and this is the donor which is forming innovate in presence of innovate. This is coming for 8-7. Very strong proof that we have also supported this hypothesis by doing NMR titration, where we showed that in presence of this catalyst is formed innovate, and this catalyst is having very strong interaction with this acceptor. You can see here that in this presence of this these two reaction partners are coming together, and that closeness leads to the sigma bond formation. Again, it gets hybridized for the. We have also further extended this for the vinylogous addition on other acceptors by breaking the symmetry. I will stop here. Yeah. So this is last, I'm really thankful to all my co-workers. Because of their hard work, it is very difficult to motivate them to work on a symmetric problem. These all work, whatever I presented today is by Sanjay. And in the last, I'm thankful to funding agencies, CSIR, SCRB, DST India, and IT Delhi. Thank you. I will be very happy to take a few questions.
Yeah, thank you, Professor Singh, for excellent talk on asymmetric synthesis. So we can have just one or two questions, quick questions. Yeah, please.
Yes. Thank you. Yeah.
When you take this, I think I'm loud here.
Yeah,
I need to understand when you take these vinylics, methyl system, like in coumarin.
Yeah.
So there is no need for any base. These acts as Michael donors very easily. So what exactly is happening, and what is the driving force for the reaction that happens?
So basically, basic condition is required. When we titrated it with that, you mean to say that even without the base, it forms. It doesn't happen. We looked over there that exomethylene group, when we treat it with the base, catalyst, exomethylene carbon start appearing actually. Without the catalyst, it remains CS3. So you have to generate the innovate. Once it generates, and then the other coupling partner is basically 1,3 ketones or whatever acceptor, that brings this, it's a kind of, you can say that, molecular robot, which brings both the things together. And once that closeness of this reactive system comes, then again, sigma bond formation takes place. That's what.
Thank you.
Yeah, one more question if you have. Okay. If no more, then let us thanks again the speaker with a big applause. Thank you.
Felicitate the professor, felicitate Professor Singh with the memento. I would also request you to present the conference script.
Thank you. Oh,
And the
Josie is having with the painting, right?
And the painting by
Yeah.
Mr. Chanchal.
Yeah, nice job. Yeah. Thank you. Yeah.
Now we begin with the next speaker talk.
Yeah, this can connect it to this. Yeah.
Okay, our second speaker is Professor Ram Sagra Misra. He obtained his PhD degree in 2006 at the University of Agra, and he did a postdoctoral stay in South Korea and also at the University of Oxford. So he, just before, if I have it right, before the pandemic, took a new position as a full professor at Jawaharlal Nehru University in New Delhi here, right here. His interests are in chemical synthesis of glycohybrids and their therapeutic potential. With that, welcome, Professor Misra.
Thank you, Professor Alex, and thank you, Professor Deka. And I'm highly thankful to organizer, especially Dr. Pratibha Kumari, for inviting me and giving me this opportunity to present my work here. I'm also I would like to congratulate the Deshbandhu College for organizing this wonderful conference where speakers from all around the India and also from abroad here presenting their nice work. So as I mentioned, actually I have some very recent work, but because this conference is related to the health, so I thought put some molecules which I have synthesized a little 3-4 years back in BHU, because I was earlier in BHU, recently moved to JNU, and which are having some anti-cancer activity. Okay. So basically what we do in our lab, so we are trying to identify some privileged scaffolds. And what are the privileged scaffolds? The molecule which have some biological targets, which have some biological activity, and trying to conjugate those privileged heterocycles with the carbohydrates in the interest to increase the bioavailability, to increase the stability, and to increase the solubility. Okay, and those molecules we are naming as a glycohybrids. Okay, so and then looking their different biological potentials, and also sometime we found they are active in the into the material science as well, like in the purification of water. So these two work which are mentioned here, which is little older one, which are presenting in this particular conference, where we identified some 4-hydroxycoumarine derivatives and conjugated them with the 2C-pharmyl glycals by using very efficient organocatalyst like pyrrolidine, and got the scaffolds. Okay, so the first work was done by Dr. Chintam Narayana, and this is related to this tetrahydrocarbazole and carbazolones. And why tetrahydrocarbazolone, carbazoles and carbazoles are privileged scaffolds? As Professor Rama Sastry and Ravi Prakash already mentioned, these scaffolds are very important scaffolds. They are present in many natural products. Okay, and many biologically active compounds, and especially those isolated from the family called Rutaceae, like these alkaloids, miraquinone A and pyroquinolone A and B. These are the molecules, natural product molecule, which having the carbazolone skeleton. So we identified this as a privileged scaffold. Okay, I hope I am able to convince all the students what is the privileged scaffold. Means having many biological activities naturally occurring in the nature. And these are some examples where you can see these are the tetrahydrocarbazolones, like this molecule. This is drug molecule are currently used, and surazolone A, which is also having the tetrahydrocarbazolones, and this is recently isolated in alkaloids which having anti-cancer activity, and this is also having the tetrahydrocarbazolone skeleton. And these are some other molecules which are having carbazoles. Okay, and this is the molecule from the GSK, the British pharmaceutical company, which is also having very potent anti-cancer activity. So for this scaffolds, there are many synthetic methods are available in the nature, because I am not the first one who are making these molecules. Making this scaffold, many synthetic methods already known in the literature. Most popular on the Fischer-Indole synthesis, and which you can have this kind of skeleton and then just make this carbon-carbon bond and get this molecule, or there is some like oxidative cyclization, or having this kind of precursor and then doing the Heck reaction, connecting this alpha carbon to this halide substituted derivatives. And so what we have done, we have we have planned to make this scaffold by like doing some reductive cyclizations starting from this precursor. And in this precursor, what was the unique, which what we designed, that this scaffold having the chiral centers, and which are we are not making those chiral center, rather we are inheriting those chiral center from the nature. Okay, so we're starting from the glucose, galactose, and mannose. We are making these derivatives, and we plan to make this kind of precursors, and then doing the reductive cyclization, this nitro into amine, and then just doing the Michael type of addition, give this product. But one I will show you in the coming slides. While you are trying to do so, maybe this amine can react here. Okay, 1-2 fashion, and you may get other product. Okay, so these are some examples of making tetrahydrocarbazolones. Very recently has been published, and in the present work, as I mentioned, it has 3 chiral centers and tetrahydrocarbazolones, and we use pinacol as a green reducing agent, and under microwave condition or thermal condition we were able to make this particular scaffolds. And these are some advantage of this particular methodology, like we use the green reductant molybdenum complexes as a catalyst, which is relatively less toxic and very shorter reaction time within 15 minutes, and chirally enriched polyhydroxy substituted tetrahydrocarbons we were able to make. Okay, this was our retrosynthetic plan. As I mentioned earlier, we made these carbohydrate precursors starting from glucose, galactose, and mannose, and we thought coupling these with these ortho-nitro bromo derivatives under Ullmann coupling, get this precursor, and then follow the reductive cyclization. Very simple approach. And this is the synthetic plan for making these alpha-hydro derivatives. This has been reported from previous group in CDRI, these precursors. And if you see what is the difference in these precursors, almost same synthetic pathway, like protection, deprotection, and then doing the elimination and followed by this Fourier type 2 rearrangement and then oxidation, you get this particular product. Starting from glucose, mannose, or galactose, you have all different combination of stereochemical diversity into the molecule. Once we have this substrate in our hand, we try to couple these by under standard Ullmann coupling reaction condition, and under this condition, we were able to make these precursors in good to very good yield, and this reaction works under microwave as well as under thermal condition. Thermal condition was already reported, so we were just done the microwave condition within 20 minutes. Once we got these precursors in our hand, next was to optimize the reaction condition in order to selectively reduce this, and this must react to this position, okay, rather than here. So we tried different reaction condition which are mentioned in this particular slide, and if you see under molybdenum catalyst by using pinacol as a reducing agent under toluene condition at 130 degrees centigrade within 15 minutes, we were able to make this product as a 70% isolated yield. This reaction also works by using other reducing agent like triphenyl phosphine. The yield more or less was comparative, but you know triphenyl phosphine, when you use the triphenyl phosphine as a reducing agent, you generate triphenyl phosphine oxide, which is very difficult to purify, and also this is not atom economic. So we claim that pinacol is the better reducing agent. And after having optimized reaction condition in our hand, all different, we look the substrate scope for this transformation, and if you unsubstitute an electron withdrawing groups and electron donating groups, and like nitros, CF3, all sort of substitution was well tolerated for this transformation, and we were able to make the compounds in good to very good yield. And one of the compounds was actually crystallized, which was 31 here. This one particularly, this compound was crystalline, and the X-ray was taken, and the structure was well established through the proton NMR. And this is the plausible mechanism for this transformation. We propose that this nitro derivatives, this nitro derivative undergo reduction by using this catalyst, gives this kind of this derivative, and then D in the presence of this catalyst makes our desired products, and followed, and also during this reaction the acetone was getting generated from the pinacol, and as a and acetone you can simply remove. You don't need any, for the acetone removal we don't need any column chromatography. And then we look the synthetic application of this transformation, because you might see here in my that most of the substrate were benzyl protected. So then someone might think, okay, because this reaction is working because you have very electron rich enone system, and which is facilitating this transformation. So we thought doing this reaction onto the electron deficient system also. So this the all benzyl was then removed, and then install the acetyl group, which is a very standard protection deprotection chemistry in carbohydrate, and then we perform the reaction using our optimized reaction condition, and this was successfully works, and we got this reaction working in electron deficient system as well. And we look for another application where we remove all the benzyl groups, okay, in order to, because I'm by training I'm medicinal chemist, so we always looks, okay, what's medicinal aspects we can introduce into the molecule. So there is a Lipinski rule of 5 where making amphiphilic molecule which having the balanced hydrophobic and hydrophilic system is important. So we remove all the benzyl groups and got all hydroxy there. So this part of the molecule is hydrophilic and this is hydrophobic, very balanced following the Lipinski rule of 5. And then we were also interested to make the tetrahydrocarbazoles, because carbazoles we already made in the, as I shown in previous slides. So we try to find out different reducing agents like zinc dust, iron powder, and a few of the methods are reported for this kind of transformation, but they didn't work. Then suddenly the Rene nickel and methanol, by using hydrogen gas, in 3 hours we were able to make the tetrahydrocarbazoles as well. And this is the substrate scope for the tetrahydrocarbazoles. All the reactions having working fine, electron withdrawing, donating groups without any problem. And then we were able to make the ring contraction on tetrahydrocarbazoles to make this kind of a spiro compound. That was synthetic application. Interestingly, we were interested to oxidize this particular position, okay, to make another isomer of tetrahydrocarbazolones, which than the earlier one, but the debenzylation followed by oxidation happens at this particular sites, and we were able to get the compound number 43. When we submitted this manuscript for publication, the referee asked, okay, you have shown many privileged scaffolds which having the N-methylated derivatives, and this methodology you are proposing, you are doing onto the where N is unprotected. How about doing into the N-methylated one and showing one application for the natural product synthesis? Okay, so we identified this natural product which could get simply prepared from a precursor 55. This precursor was synthesized in my laboratory, and then followed by our methodology, we were make this 56 compound, and then 2 known steps, we got the final compound. And this is how this work got published in Organic Letter. And so in summary, we have, by using the same precursor, by using different reaction condition, we were able to make tetrahydrocarbazolones and carbazoles. And another work published in OBC, where we identified this pyronoquinolones as a privileged scaffold. Just remember my first slide, privileged scaffold conjugating with the carbohydrate. Okay, so these pyronoquinolones, they are present in having different biological activity like anticoagulant, anti-tumor, anti-hypertensive, and many more. So these are a few examples where A, B, C, D, you can see these alkaloids are naturally occurring alkaloids. They have some biological activity, and few of the molecules, especially this one compound number B, which is genthosumulene. This is a molecule which is anti-cancer against the drug-resistant cancer cells. Okay, so we design molecule like F, where you have pyronoquinolones along with the carbohydrate moiety fused to it. Okay, and this we named as a new carbohydrates. So this is our synthetic plan. So we plan, okay, having this 4-hydroxyquinolone as a precursor, and then conjugating these one, and this reaction might work via go C12 addition followed by 6-pi electron electrocyclization may give this particular product. And while this product is forming, a new chiral center is generating, so there might be some stereoselectivity or there might be no stereoselectivity. So these 4-hydroxypyronoquinolones are not commercially available. So starting from this aniline derivatives and this by using the Eton's reagent, we were able to make these 4-hydroxyquinolone derivatives. The synthetic methods is already known in the literature, but we modified bit and got these compound 1 to 11 in good to very good yield. And then these 4-hydroxyquinolones were subjected for the condensation reaction by using 2-C-pharmyl glucal and 2-C-pharmyl galactal by using different reaction condition. And if you see different organocatalysts like pyrrolidine, piperidine, proline, they have been tried. The best condition was the pyrrolidine and then ethylacetate solvents at 80 degrees centigrade. Within 15 minutes, we were able to make this compound in 71% isolated yield. And interestingly, the new chiral center which was generating here, and this we got only one diastereomer. Okay, so that means this reaction was stereoselective, diastereoselective. And after having optimized condition, again the library of compound was synthesized with all different substitution, like if you see nitro and fluoro or even OCF3 and also some donating groups. Okay, like this one ophenyl here, and the yield was good in case of nitro. In case of this OCF3, yield was relatively less, only 55% yield. And this is our proposed mechanism for this transformation. We propose that pyridine makes this iminium salt, and this basically activating the aldehyde group, and then making this carbon more electrophilic, and then this 4-hydroxyquinolones, the C3 position, which is nucleophilic in nature, attacks over here, and got this particular intermediate 3, which after like rearrangement making this hydroxy derivatives, and which after beta elimination makes the 6 pi electron system, which is called 1-octatrine, which undergoes 6 pi electrosalivation, gives the final product. Okay, and then similar reaction was tried with the glucal derivatives, and it worked perfectly fine. There was no problem. And then once we got this compound, we subjected these molecules in collaboration for the testing for their anti-cancer activity against 2 cell line. One is MCF7 and HG2 cell line, and the results are here. The selected compounds, they have the anti-cancer activity at the sub-micromolar concentration. I would not say this is very great anti-cancer activity because it's not up to nanomolar, but still we got some lead compounds which having the sub-micromolar anti-cancer activity. And this is one of the N-methylated derivative which has been prepared by adopting the similar methodology. In summary, we have shown that 2C-pharmyl glucal or galactol can successfully coupled with the 4-hydroxyquinolone derivative under very mild reaction condition, and we got very diverse privileged scaffolds having the carbohydrate fused pyranoquinolones in good to very good yield, and these selected compounds having the sub-micromolar anti-cancer activity. So in conclusion, we have developed regioselective synthesis of chirally enriched tetrahydrocarbazoles and carbazolones, and also we have developed the efficient method for the synthesis of pyranoquinolones and selected compounds having anti-cancer activity. Okay, with these words, I would like to thank Sir DST for their financial support. And as this work was actually done in Banaras Hindu University, so their facilities, I'm very thankful. And Dr. Ashish Gupta for evaluating these molecules for their anti-cancer activity. And Chintam Narayana, he actually done the previous work which published in Organic Letter. Dr. Preeti Kumari, the work was published in the Organic and Biomolecular Chemistry. And can I have 1 minute? Just this is my recent lab which we have developed at Jawaharlal Nehru University, where I have recently moved. So very initial phase. This is the first batch of chemical when arrived. I was very much happy here. And these are some few visitors. These are my students. First rota web, made in India. Okay. And then this lab was inaugurated by our Vice Chancellor. And this lab was actually, funds was given by this Saint Sagnaria and there are few other visitors. And thank you very much for your kind attention. I'm happy to answer any questions.
Thank you. Thank you so much. I think we could take a question or two.
Yeah. Huh?
You have the slide number, but you have a mechanism of molybdenum reducing influence of phenocol. Can you please go to that
Yeah,
slide?
sure. Can you activate this? Just put ESC, then I will escape kar do aap. Go up. Slide number I think 12.
Yeah, I because slide number is not visible from here, so
Yeah. So 14.
Yeah, 14. Yeah. So here you're showing nitro going to nitroso.
Yeah.
I'm not sure how that goes. I mean, deoxygenation occurring. Second, the nitroxide nitron going to amine. There also how that deoxygenation occurring. It's not clear.
From
And
here, how
what
the
is the role of phenocol exactly here in the mechanism is another question.
Okay, so yeah, it's a good question. So what we propose, like this nitro group, one of the oxygen is getting taken by this molybdenum catalyst. Okay, so you are saying how nitro going nitroso and nitroso to this particular one. That we have to look, because this was we proposed and referee accepted, then got published. So this is only proposed mechanism. Yeah, this is what we have wrote. Actually, this is 4 here, and this here is. We'll look on this. Yeah, thank you for your question. Yeah.
Okay.
Carbohydrates,
Hmm.
that is of glucose, mannose, and galactose,
Hmm.
right? Have you tried for aldose and ketose hydrates or ribose or hexose hydrates? Or the hydrates are of same class?
Yeah, no, actually, if your question is from the first part of the my presentation, so in that case you have to have alpha idoinone derivatives. Okay, so those alpha idoinone derivatives we have prepared from glucose, galactose, and mannose. Same can be prepared from ribose also. Okay.
We have to try it from within the same class only. Like if we are trying from the aldoses, they have to be tried from the aldoses and that too within the hexoses only. We can't mix match the things like ribose with the hexose or ketose with the aldose.
Yeah, so until like as far as you have this kind of system, okay, you have chosen the right precursor. If you're able to get this one, this undergo Fourier type 2 rearrangement, and you get this molecule and do the iodination here.
This can be also in the ketose and the aldose. They
Yes,
also have the same kind of.
yes, exactly. This can happen from there also.
Have you tried it?
No, I haven't tried. I have only 3 precursors: glucose, galactose, and mannose.
Okay, let's thank Dr.
Thank you.
Saga.
Thank you very much.
Once again, thank you so much.
Answer to your question, Ramasastri. Can I move next slide? I got answer of your question.
Thank you, sir, for your interesting talk. Now, I would request Dr. Alexander to felicitate our speaker with the memento. And with the conference kit. And the painting.
Okay, we're on to our third talk. The next speaker is Dr. Pooja Panwar Hazari. Dr. Hazari is currently a biomedical scientist, the cyclotron and radiopharmaceutical sciences. She received her PhD degree from Delhi University in 2006, and she received an award. I was kind of intrigued by the name of the award, Catch Them Young Scholarship. As some of us are aging, I kind of like that phraseology rather than probably what would apply to some of us at this point. But she's an expert in radiopharmaceuticals, PET imaging, and other related areas. Particularly intriguing to me are the radio labeling of small molecules containing carbon-11, fluorine-18, oxygen-15. Very interesting, intriguing work. So look forward to your talk.
So thank you very much, Dr. Alexander, for that introduction. I just told you that just give the title of my talk. That's it. That's my introduction. So, turning the cyclotron for the production of designer radionuclides, paving the path for theranostics. So, okay. So, here, what is theranostic? Theranostic is a very interesting word, and if you add radio to it, it becomes radiotheranostics. So, we would like to be, this to be an interactive session. I want students to stop me in between if they're not, getting any further. So, if you see this, So INMAS is a hub for or a center for advanced molecular imaging, and it has already demonstrated its diagnostics capability in determining the various malignancies in the patients at our center. So all these drugs that you can see, which are labeled either with fluorinating or with carbon 11, are being injected into patients, and we are able to know about the lung malignancies, breast carcinoma, liver malignancies, prostate carcinoma, skeletal metastasis, and so on. And obviously the neurocognitive disorders that we have done with dopamine, which is also labeled with fluorinating. So you can see here, this is the F choline, and it is missed on a lot of biochemical tests, PSA test, and other modalities. This is the only modalities. Now you would be thinking that why radiotheranostics is there when we have the therapeutic drugs, we have the therapeutic molecules, we have been treated with those antibiotics. Then why the need of this molecular imaging? See, when molecular imaging is something which you see, which you can see, which you can substantiate, which you can quantitate in terms of receptor. So we do receptor imaging, and it's the road to, you have heard about the pharmacogenomics as the road to personalized medicine, but nuclear medicine in some way is a path to personalized or precision medicine, because you can quantitate the receptor in the body with the tracer uptake, and then you can also optimize the drug being given to the patient for therapeutic treatment, or the monitoring or the disease monitoring could also be possible with diagnostic imaging agents. So why radiotheranostics? Already we have diagnostics with so many molecules. Now why we want to enter into radiotheranostics? Because when you see that when you can see it, then also you want to treat it. When you can see it, the treatment becomes much easier because you know what to target and where to target. So here targeted radiotherapy, which we see is successfully done with the short range emitters, which are alpha and beta. And basically, the diagnostic imaging that you do is with the photons that are being emitted, or the gamma emitters, or the photon emitters, which is the positron emission tomography, which is called the PET, and with the gamma photon, it is called a single photon emission computed tomography, right? So for the theranostic radionuclide, you can do the therapy when you change the metal ion or the radioactive element by the alpha, beta, or the Auger. And at the same time, when you are using it for diagnostics, you can change the radioisotope to be a photon or gamma emitting. So theranostic match pairs is really utilized to minimize the differences in the chemical behavior between the compounds which are being administered to the patient. So while also simplifying the synthesis of such compounds, because you do not need to change the precursor or the biological active molecule in that case, only you need to change as a radionuclide. So here you can see that what are the fundamental of designing a radiopharmaceutical. We need to have the target, what we are seeing, what we want to visualize. In different pathologies, different receptors are overexpressed. Like for example, folic acid is expressed in most of the oral carcinomas and cervical carcinomas. And if you see the other one, like the neurocognitive disorders, there is a plethora of receptors or the neurotransmitters like 5-HT1 as a serotonergic, dopaminergic, acetylcholinergic. These are systems could be utilized as a target for assessing the neurocognitive disorders in the brain. Here you can see that once the target is identified, then we take it to the lead compounds and we subject it to molecular modeling at various targets. And when we see that, yes, this is working fine with the receptor or the docking or the molecular dynamic simulations, we take up for the synthesis, we design our molecular probes based on that, and then we establish a synthesis and the purification process for that particular molecule. And after that, a radiochemical pathway is designed for that, or the radiochemical synthesis is designed for that particular molecular probe. Again, it subjects to various battery of tests like the preclinical evaluation, in vitro cellular studies, cytotoxic profiling of the synthons, and then the prostate groups and the conjugates on experimental and animal models. After that, we do the preparation of the animal models of the brain or do the dynamic studies and the biodistribution. And after getting the ethical clearance, we subject it to human evaluation. So we have a very defined methodology. We do a lot of preclinical studies, and then after that we go on to the clinical. So this is the whole plethora of facilities that we are having at our center, starting from the molecular modeling facilities, and then the wet chemistry and the nano lab, where we have the all kind of analytical tools. Then the radioisotope production facility, where we are housing a 16.5 mega electron volt cyclotron with a solid external beam line, where we can do a lot of radiochemistry out of that. And you can see that the preclinical research facility is also there. We have the animal imaging, so that whatever we are injecting, whatever we are making or doing the synthesis with the radioisotope, we do the imaging. And then after that, we have the clinical research facility and the same umbrella. We have the 3D MR, PET CT, and SPECT. So everything we are doing at the same institution. So here, why we want to work on the theranostics. Like theranostic means that I told you that when you are using the alpha and beta, it is utilized for the therapeutics. When you use the gamma, it is utilized for the imaging applications. But what if you get all these things in one radioisotope? That is the copper 64. Copper 64 is a beta emitter, which is beta negative. It is also a positron emitter. So at the same time, you can do the imaging as well as the treatment is also happening at the same time. So we are looking forward into those kind of radioisotopes or the radionuclides which are not available here, and we can make these kind of systems available in the country so that we can simultaneously track and treat the disease. So this is the example of the PRRT, that is a peptide radionuclide receptor therapy. So you can see that I have done gallium, scandium, copper, and 90, and slash slash slash. DOTA peptide is the same. So what you can do is you can change the type of peptide, you can change the radioisotope according to the application, but your DOTA will remain the same. That is the macrocycle, polyamino, polycarboxylate macrocycles are there, which house or which in that cavity there is a complexation of gallium or scandium or copper or yttrium 90. So according to the chemical environment present around the radioisotope, we design our macrocyclic system, and then you can change either your peptide or change either your radionuclide. So we intend to produce all these radioisotopes, gallium, scandium, copper, and yttrium on our cyclotron system. And here you can also see that PSMA, prostate, very small molecule, that can also be utilized to treat prostate cancer. Lutetium 177 is a good example, which is radio complex with PSMA, and then it is being utilized for the treatment of the prostate cancer. So here you can see that this is the cyclotron housed in the mass facility. Then this is the automated GMP production, and there's a synthesis module which is fully automated, and some are semi-automated where we design our protocols. We do the cold synthesis, we run the synthesis, we simulate the synthesis, and then we turn that into an automated synthesis in this module. So we have a very good real-time radiation monitoring system of the cyclotron operations, because a lot of radioactivity is there, so we need to be monitored regularly. And since we have a robust system, so we don't get any kind of radioactivity when we're working on this kind of system. So advanced radioisotope that already we have produced are fluorine 18, carbon 11, N13, that is ammonia, O15, and the half-life, they are having very short half-life because they are used as a diagnostic radionuclides. F18 having the short half-life of only 110 minutes, carbon 11 is only having a half-life of 20 minutes, and 13, 14 minutes, and O15, which is oxygen 15, is only having a half-life of 2 minutes. So we have done the scanning of all these radioisotope in patients, and with O15, it's very highly, because 2 minutes is the half-life, so you have to have some time for scanning as well. So we have the delivery line which is going directly from the cyclotron to the patient. So we deliver the oxygen 15 to the patient, and you can see the perfusion imaging going on for 4 hours or 5 hours to see the perfusion of oxygen 15 in cardiac imaging, right? So now the production of high purity radioisotopes, you can see here the scandium, titanium, copper, gallium, yttrium, zirconium, iodine. These all are radioisotopes that are metal based except from the iodine, which is halogen. Here you can see that scandium is having a half-life of 3.97 hours. Then titanium is also having a good half-life. Copper is 12.7. Gallium 68 minutes. Then zirconium 3 days. Iodine 3 days. This kind of radioisotope which is having a high half-life and having a dual modality, like you can do the imaging as well as the therapeutics. This is what we are going to start. We have already produced cadmium and copper in small quantities for research applications, but now we are gear up for the high scalable production of these radioisotope. So in the solid targeted system, we intend to produce all these radiometals for further applications. So now the question is how you generate fluorine-18 in the system. So it depends upon the targets, right? So our cyclotron is having the solid, liquid, and gaseous targets. On the liquid targets, when the target is oxygen or the O18 enriched water, if you bombard with proton, there's a PN reaction happens, and that PN reaction, what will happen? F18 is produced. And if you see about carbon 11, you can see that nitrogen balanced with oxygen is used, and then again there is a PN reaction, you will get carbon 11. Then after that nitrogen again, if you want to produce oxygen 15, then you have to have the enriched target as a nitrogen, and then you bombard again, it's a PN reaction, and the half-life is 2 minutes. And F18 or the fluorine gas, you can produce fluorine gas also in the form of the neon. If you bombard neon, you can get is the gaseous target. You can get fluorine 18, which is in the form of gas, and F2 molecule, which is electrophile. And when we using the fluoride ion or the oxygen 16 or oxygen 18, then you get the fluorine 18. So this is the cyclotron production of fluorine 18. You have the two methodologies here, either on the liquid phase or on the gaseous phase. You can use the liquid target as well as the gaseous target to make the fluorine 18. And then you can see that this is the chem module where we do the simulations and all. So here, when we bombard the O18, we get the F18. From the cyclotron, we get the F18 into the module. When it comes in the module, you can see that this is the reactor vessel. Here is the reactor vessel, and now the fluorine 18 is here, which is radioactive, and then it goes with a cartridge, because this is the oxygen 18 also will be present in the F18 mixture, so we have to separate it. It is separated by a QMA cartridge, which where cryptofix and trapment is there, and cryptofix takes the fluorine 18 and gets into the another reaction vessel where the precursor is there, and then when it reacts with the precursor, and then after the end of the synthesis, we subject it to HPLC purification. You can see that in the same module you have the HPLC as well. Then after the HPLC is there, we get the purified product in this vessel, and this is ready for injection to the patient. So this is one of the case that with the fluorine 18 that we have developed. We have labeled fluoroethoxytyrosine, and then again same with the semi-automated module, we have changed it to the cartridge purification because time is the constraint. So we have to develop a methodology where you can do the reaction in 10 minutes or maybe 15 minutes, not more than that, because we need to save the time. So here we what we do is we convert this HPLC methodology into the cartridge purification using the different cartridges like TC18, alumina cartridge, HLBOSS cartridge. So a lot of purification cartridge we employ, and we get the purified, which is again the batch is checked on the radio HPLC that we are having at our center. So all the quality parameters, all the quality control is being done before we inject into the patient. So this is the first PET MR study with fluoroethoxytyrosine in the country. You can see that there is, this is the conventional MR scan where you can see that there is some abnormality seen over here. But in the PET scan, if you'll see, there is a recurrence of the oligodendroglioma, which is the post-operated. This was previously this was operated, but the recurrence is there, but it is not shown on the conventional MR. But if you see that the uptake is so good for this target LAT1, which is overexpressed in the gliomas, so it goes and binds on the LAT1 transporter, and it Somehow it delineates the tumor and it is very beneficial to the neurosurgeon so that he can take out all the viable cells from inside the brain. So now coming to the carbon 11, as I already told you that you have to have nitrogen balanced with oxygen to get carbon 11, and then carbon 11 reacts with oxygen to become CO2, carbon 11 CO2. Then we have in this chamber, if you see that this is a short synthetic module that we are having. So this is the chamber where we are having the nickel light, and it works on the 350 degrees centigrade. And after that, there is a furnace where iodine sublimation is there, which is goes up to 750 degrees, and all the reactions are in the gaseous form. Methane is formed after the nickel light, and after that, the methane is converted into an alkyl for the alkylation. So here alkyl halide is there, and then this reacts with the homocysteine thiolactone when the bond is. So here you can see the iodine oven and all. And once we get the methyl iodide, it is reacted to the homocysteine thiolactone to get the required precursor. Then again, it is subjected to purification to isolate this particular compound having a very high specific activity. And you can see and appreciate the good uptake in the gliomas for this particular molecule. So this is the other methodology that we have developed with carbon azide, carbon 11 azide also we have prepared for the click reaction. Any biomarker interest can be labeled with this kind of module and this kind of alkyl azide, where we are having the terminal alkyne. It can be labeled with azide, methyl azide. So now the beamline for the solid targetry, how copper is produced. So we have the nickel as electroplated material, which is enriched. 95% enriched or 99.2% enriched material is being utilized for the production of the copper, which is having a half-life of 12.7 hours. So this has a great chemistry. We need a lot of macrocyclic molecules and for the copper complexation. So we are developing a lot of them based on CXCR. So why is chemistry so important? Because it's a critical criteria for your equipment or for your labeling methodology. Give you the tracers of high yields, reproducible production, and minimize the radiation exposure as well. So here we have also produced scandium in conjunction with our PSI ETH Zurich. So here we are doing the production of the scandium 44, and we successfully produced. And though in the research quantities, we are now gearing up for the scalable production of the scandium 44. So that this is an acknowledgement. I would like to acknowledge my then director, because he's retired just now, Dr. Anil Kumar Mishra, Dr. Shubhra Chaturvedi, Dr. Maria, she is a clinician, and our ARPC team, that's the Advanced Radioisotope Production team. Thank you very much.
Thank you very much. We have time for a couple of questions. So.
Yeah, a very nice talk. So I have one, I think, the layman question. You said about copper 64, right? So copper 64, when you have beta
Negative.
and positron. So and you said 2 application, right? So whether the one particle will not interfere the other application, say positron will not affect your imaging.
Yeah,
or
because
beta will not affect your I think otherwise medical, right? So that's it.
So when we are talking about the diagnostic application, we need to have a scanner, like we need to have a detection methodology for that. So photons are detected onto that. So beta negative is not detected on the PET camera. We are using the avalanche photodiode for detection of these in the 360 degrees they are placed, and they are able to capture the photon and not the beta negative. Beta negative is not high, it's a low LED radiation, right? Gamma is highly penetrating. When positron is annihilating with a matter, it is producing photons in 180 degrees. So you have a photon in 180 degrees, 2 photons will be there. So they will be ejected, and they will be captured onto the onto the detectors, which are the avalanche photodiode. And when you talk about the beta negative has a low LED radiation, like it deposits its energy where it is reaching. So it will deposit its energy into the cell. So it will not come out, the energy or the range is not so high that it will penetrate everything and goes out. So beta is stopped. You can you have already know that the beta you can stop by plexiglass or something which is not of lead. But if the photons, as far as the photon goes, you need to have a HVL of 110, like the lead, tungsten. They are only the material that can stop the gamma radiation. So that is how you can use even the copper 67, which is used for SPECT imaging. It emits single photon, and then it is also it's emitting beta. So this that can also be utilized for the both simultaneous theranostic, I would say. Then there is another methodology called the sequential theranostics that I've shown in my previous slide, that you can use gallium, which is emitting your only positron, that is utilized for the imaging application. And if you change gallium to lutetium, that is then, or actinium 225, or astatin 211, that is purely alpha emitter. So that way you can do the therapy. But first you need to know that my targeting vehicle or the peptide receptor that I'll be using, it is going there or not. And you need to also check the tumor to background ratio to have the effective radiotherapeutics to be done. So it will have a good effect if you are using like simultaneously also, and the dose will be different. Like we do the biodosimetry for if I want to treat a patient with a beta negative, I need to do the dosimetry of that particular radioisotope, that how much I'm going to inject. See, here for FDG, we are injecting only 10 millicuries of the radioactivity. Somehow, if I'm going to have the therapeutic application of the beta negative, I might have to inject more than 10 millicurie according to the biodosimetric calculation of that particular beta emitting radioisotope.
I think one more question, and then we'll wrap it up. So
I just want to ask one question. I have one query. Like, is there an application in therapy, cancer therapy, like cancer therapy?
Yes, this is all cancer therapy only. Like
But I have not seen the slide where the molecules are traced, like the localization of these molecules, whether actually it is reaching that target. So if that is possible, if it is reaching that, because there are some cells which are living also.
yes, that is why we want to
So
first, because we are when we are doing the diagnostics, we are injecting only the tracer quantity, right? We are injecting to the power of like in nanograms we are injecting, and the nanocuries also millicurie we are injecting, which is in the permissible limit. And if you see the biodistribution of the tracer kinetics, and we do the biodistribution as well when the patient is in the scanner, we do the biodistribution of that particular tracer. And we see that for the most of the molecules, because they're the small molecules, they don't have the long circulating time inside the blood. So they clear from the body very easily, and it reaches to the target and entraps there, like fluorodeoxyglucose. What happens in that? So
it will reach the target as well as it will reach the living cells also, healthy cells also.
healthy cells, vis-a-vis, if you have the receptor, substantial amount of receptor concentration of that particular targeting vehicle in the normal cells. For example, folic acid receptor. So if you have in normal cell, if you have one expression in the living cell, then in the cancerous cell, the amount will increase to 20,000 or maybe 40,000. And the amount of, because the receptor recycles back folic acid to gain more and more, folic acid at the target site. So recycling of the receptors also result in the increasing the payload at the target site. So the target concentration at the cancer site will increase. So we have to see the benefit to risk ratio also, that uh, normal versus my cancer cell. I want to kill my cancer cell, and
With very limitations in normal cells, like
yeah, very limited, which is not going to affect or kill that normal cell. This is what it's the beauty of molecular imaging, that you can see it and you can treat it. Like for example, I'll give an example. It's a very good example wherein FDG is fluorodeoxyglucose. You know that fluorodeoxyglucose goes in inflammation, infection, any kind, wherever there is hypermetabolism, FDG will go and sit over there. Even in the brain, you'll find the whole brain is, I don't know if I'm having the FDG picture or not. You'll find that the whole FDG uptake you can see in the brain. So what is the consequence of that? You'll miss out the small tumor that will be there in the brain because of the FDG uptake, because you can only find the FDG uptake in the whole brain. So what we do, you can see that this is the picture of the brain, where we have injected a very specific LAT marker, or the F-DOPA, which goes on to the LAT1. LAT1 is overexpressed in the tumors. You'll not find the uptake in whole brain. You'll find only at the places where the viable cells are there. That happens in the fluoroethoxytyrosine as well. That is how the doctors are able to, delineate the tumor. I'll show you the picture. You will
highly recommended for brain.
no, not brain, neuroendocrine tumor as well. Neuroendocrine are very rare kind of a tumors, where you cannot, detect even in the choline cases. If you can see the first slide of ours, prostate cancer. So here you can see this. This is a lesion of the prostate cancer. It will miss out on any of the MR, CT. You'll not find out. And even in the PSA antigen, where you do the biochemical markers, there also it is being missed. But on this imaging, with this kind of small, very small, 1 to 2 mm tumor, it is only possible to get on the molecular imaging. Now this will become a standard for doing the therapeutics. Now I know that there is a tumor over there. Now I can subject this patient to lutetium 177 PSMA therapy, which is now available, very well available in most of the hospitals in India. And Bark is also supplying lutetium 177, where they're getting very good results on the prostate carcinoma.
Okay, I think we need to wrap it up. So thank you so much, Dr. Hazari.
Now I would request Professor Greaves to come and felicitate the speaker with the memento, conference kit, and painting.
So I really love this painting, and I could see, when I was sitting over there, I could see so many microcycles in there, and I could see that there are my metals. So this is great. Thank you.
Now I would request Professor Chauhan to felicitate our chairperson for the current session, Professor Deka and Professor Greed. Can we have the mementos, please? Conference. Now, I request Professor Chauhan to felicitate Professor Deka also with the memento and conference kit. Now, to summarize the session, we have quite interesting talks on approaches for induction of chirality by desymmetrization, stereo-selective synthesis of natural product-inspired carbohydrate fuse hybrid for the biological applications, and churning the cyclotron for the production of designer radionucleotides. Now, I would request everyone for a tea break for 15 minutes and kindly assemble here again for the next session on the oral presentation. Thank you very much.